In linear algebra, functional analysis, and related areas of mathematics, a norm is a function that assigns a strictly positive length or size to each vector in a vector space, save for the zero vector, which is assigned a length of 0. A seminorm, on the other hand, is allowed to assign 0 length to some non-zero vectors. A norm must also satisfy certain properties pertaining to scalability and additivity, which are given in the formal definition below. A simple example is the two-dimensional Euclidean space R2 equipped with the Euclidean norm. Elements in this vector space are usually drawn as arrows in a two-dimensional Cartesian coordinate system starting at the origin. The Euclidean norm assigns to each vector the length of its arrow. Because of this, the Euclidean norm is often known as the magnitude. A vector space on which a norm is defined is called a normed vector space. Similarly, a vector space with a seminorm is called a seminormed vector space. It is often possible to supply a norm for a given vector space in more than one way. Definition: given a vector space V over a subfield F of the complex numbers, a norm on V is a function p. Vr with the following properties. For all F and all U, P equals A, P, PP plus P. If P equals 0, then V is the zero vector. By the first axiom, absolute homogeneity, we have P equals 0 and P equals P, so that by the triangle inequality P0, a seminorm on V is a function P. Vr with the properties 1 and 2. Above, every vector space V with seminorm P induces a normed space V, W, called the quotient space, where W is the subspace of V consisting of all vectors V and V with P equals 0. The induced norm on V, W is clearly well defined and is given by P equals P. Two norms P and Q on a vector space V are equivalent if there exist two real constants C and C, with C greater than 0 such that for every vector V in V, one has that CQ. A topological vector space is called normable if the topology of the space can be induced by a norm. Notation: if a norm P, Vr is given on a vector space V, then the norm of a vector VV is usually denoted by enclosing it within double vertical lines. V equals P. Such notation is also sometimes used if P is only a seminorm. For the length of a vector in Euclidean space, the notation V with single vertical lines is also widespread. In Unicode, the code point of the double vertical line character is U plus 2016. The double vertical line should not be confused with the parallel to symbol Unicode U plus 2225. This is usually not a problem because the former is used in parenthesis-like fashion, whereas the latter is used as an infix operator. The double vertical line used here should also not be confused with the symbol used to denote lateral clicks, Unicode U plus 01C1. The single vertical line is called vertical line in Unicode and its code point is U plus 007C. Examples: all norms are seminorms. The trivial seminorm has P equals 0 for all x in V. Every linear form F on a vector space defines a seminorm by X, F. Absolute value norm: the absolute value is a norm on the one-dimensional vector spaces formed by the real or complex numbers. Euclidean norm on an n-dimensional Euclidean space Rn. The intuitive notion of length of the vector x equals is captured by the formula. This gives the ordinary distance from the origin to the point x, a consequence of the Pythagorean theorem. The Euclidean norm is by far the most commonly used norm on Rn, but there are other norms on this vector space as will be shown below. However, all these norms are equivalent in the sense that they all define the same topology. On an n-dimensional complex space Cn, the most common norm is in both cases. We can also express the norm as the square root of the inner product of the vector and itself, where x is represented as a column vector, and x denotes its conjugate transpose. This formula is valid for any inner product space, including Euclidean and complex spaces. For Euclidean spaces, the inner product is equivalent to the dot product. Hence, in this specific case the formula can be also written with the following notation. The Euclidean norm is also called the Euclidean length, L2 distance, 2 distance, L2 norm, or 2 norm, CLP space. The set of vectors in Rn+1 whose Euclidean norm is a given positive constant forms an n-sphere. Euclidean norm of a complex number. The Euclidean norm of a complex number is the absolute value of it if the complex plane is identified with the Euclidean plane R2. The identification of the complex number x plus iy as a vector in the Euclidean plane makes the quantity the Euclidean norm associated with the complex number. Taxicab norm or Manhattan norm. The name relates to the distance a taxi has to drive in a rectangular street grid to get from the origin to the point x. The set of vectors whose one norm is a given constant forms the surface of a cross-polytope of dimension equivalent to that of the norm minus 1. The taxicab norm is also called the one norm. The distance derived from this norm is called the Manhattan distance or one distance. The one norm is simply the sum of the absolute values of the columns. In contrast, is not a norm because it may yield negative results. P norm. Let P1 be a real number. For p equals 1 we get the taxicab norm, for p equals 2 we get the Euclidean norm, and as p approaches the p norm approaches the infinity norm or maximum norm. The p norm is related to the generalized mean or power mean. This definition is still of some interest for 0 less than p less than 1, but the resulting function does not define a norm, because it violates the triangle inequality. What is true for this case of 0 less than p less than 1, even in the measurable analog, is that the corresponding LP class is a vector space. And it is also true that the function defines a distance that makes LP into a complete metric topological vector space. These spaces are of great interest in functional analysis, probability theory, and harmonic analysis. However, outside trivial cases, this topological vector space is not locally convex and has no continuous non-zero linear forms. Thus, the topological dual space contains only the zero functional. The derivative of the p-norm is given by the derivative with respect to x, therefore, is where denotes Hadamard product and is used for absolute value of each component of the vector. For the special case of p equals 2, this becomes our maximum norm. The set of vectors whose infinity norm is a given constant C forms the surface of a hypercube with edge length 2c. Zero norm in probability and functional analysis. The zero norm induces a complete metric topology for the space of measurable functions and for the F-space of sequences with F-norm, which is discussed by Stefan Rolevich in metric linear spaces. Here we mean by F-norm some real-valued function on an F-space with distance d, such that Hamming distance of a vector from 0 in metric geometry, the discrete metric takes the value 1 for distinct points and 0 otherwise. When applied coordinate-wise to the elements of a vector space, the discrete distance defines the Hamming distance, which is important in coding and information theory. In the field of real or complex numbers, the distance of the discrete metric from 0 is not homogeneous in the non-zero point. Indeed, the distance from 0 remains 1 as its non-zero argument approaches 0. However, the discrete distance of a number from 0 does satisfy the other properties of a norm, namely the triangle inequality and positive definiteness. When applied component-wise to vectors, the discrete distance from 0 behaves like a non-homogeneous norm, which counts the number of non-zero components in its vector argument. Again, this non-homogeneous norm is discontinuous. In signal processing and statistics, David Donahoe referred to the zero norm with quotation marks. When this norm is localized to a bounded set, it is the limit of p-norms as p approaches 0. Of course, the zero norm is not truly a norm, because it is not positive homogeneous. Indeed, it is not even an F-norm in the sense described above, since it is discontinuous, jointly and severally, with respect to the scalar argument in scalar vector multiplication and with respect to its vector argument. Abusing terminology, some engineers omit Donahoe's quotation marks and inappropriately call the number of non-zeros function the L0 norm, echoing the notation for the Lebesgue space of measurable functions. Other norms on Rn can be constructed by combining the above. For example, is a norm on R4. For any norm and any injective linear transformation A, we can define a new norm of x equal to in 2D, with a rotation by 45 degrees and a suitable scaling. This changes the taxicab norm into the maximum norm. In 2D, each A applied to the taxicab norm, up to inversion and interchanging of axes, gives a different unit ball, a parallelogram of a particular shape, size and orientation. In 3D this is similar but different for the one norm and the maximum norm. All the above formulas also yield norms on Cn without modification. Infinite dimensional case, the generalization of the above norms to an infinite number of components leads to the LP spaces, with norms, which can be further generalized. Any inner product induces in a natural way the norm. Other examples of infinite dimensional normed vector spaces can be found in the Banach space. Article. Properties. The concept of unit circle is different in different norms. For the one norm the unit circle in R2 is a square, for the two norm it is the well-known unit circle, while for the infinity norm it is a different square. For any P norm it is a superellipse. See the accompanying illustration. Due to the definition of the norm, the unit circle is always convex and centrally symmetric. In terms of the vector space, the seminorm defines a topology on the space, and this is a Hausdorff topology precisely when the seminorm can distinguish between distinct vectors, which is again equivalent to the seminorm being a norm. The topology thus defined can be understood either in terms of sequences or open sets. A sequence of vectors is said to converge in norm to if as. Equivalently, the topology consists of all sets that can be represented as a union of open balls. Two norms alpha and beta on a vector space V are called equivalent if there exist positive real numbers C and D such that for all x in V, for instance, on if P greater than R greater than 0, then in particular, if the vector space is a finite dimensional real or complex one, all norms are equivalent. On the other hand, in the case of infinite dimensional vector spaces, not all norms are equivalent. Equivalent norms define the same notions of continuity and convergence and for many purposes do not need to be distinguished. To be more precise, the uniform structure defined by equivalent norms on the vector space is uniformly isomorphic. Every norm is a sublinear function, which implies that every norm is a convex function. As a result, finding a global optimum of a norm-based objective function is often tractable. Given a finite family of seminorms Pi on a vector space, the sum is again a seminorm. For any norm P on a vector space V, we have that for all U and VV. P minus P. Proof. Applying the triangular inequality to both in. Thus, P minus P. If an unnormed space is and is a continuous linear map, then the norm of and the norm of the transpose of are equal. For the LP norms, we have Holder's inequality. A special case of this is the Cauchy-Schwarz inequality. Classification of seminorms. Absolutely convex absorbing sets. All seminorms on a vector space V can be classified in terms of absolutely convex absorbing sets in V. To each such set, A corresponds a seminorm par called the gauge of A, defined as par equals INF alpha, alpha greater than 0, x alpha A, with the property that x par less than 1, A x par 1. Conversely, any locally convex topological vector space has a local basis consisting of absolutely convex sets. A common method to construct such a basis is to use a family of seminorms P that separates points. Disambiguation needed. The collection of all finite intersections of sets P less than 1, n, turns the space into a locally convex topological vector space so that every P is continuous. Such a method is used to design weak and weak asterisk topologies. Norm case. Suppose now that contains a single P. Since is separating, disambiguation needed, P is a norm, and A equals P less than 1 is its open unit ball, then A is an absolutely convex bounded neighborhood of 0, and P equals par is continuous. The converse is due to Kolmogorov. Any locally convex and locally bounded topological vector space is normable. Precisely. If V is an absolutely convex bounded neighborhood of 0, the gauge GV is a norm. Generalizations. There are several generalizations of norms and seminorms. If P is absolute homogeneity but in place of subadditivity, we require that then P satisfies the triangle inequality but is called a quasi-seminorm, and the smallest value of B for which this holds is called the multiplier of P. If in addition P separates points, then it is called a quasi-norm. On the other hand, if P satisfies the triangle inequality but in place of absolute homogeneity, we require that then P is called a K-seminorm. We have the following relationship between quasi-seminorms and K-seminorms. Suppose that Q is a quasi-seminorm on a vector space X with multiplier B. If then there exists K-seminorm P on X equivalent to Q,